In this session, we are going to cover expansion devices used in refrigeration and air conditioning applications. Expansion devices are used to throttle high pressure refrigerant into low pressure liquid refrigerant. In other words, we are converting the refrigerant pressure, that is condenser pressure, to evaporator pressure in the expansion devices. Expansion valves are the devices used to control the refrigerant flow in a refrigeration system. Expansion valve helps to facilitate the change of higher pressure of liquid refrigerant in the condensing unit to lower pressure gas refrigerant in the evaporator. There are three types of expansion devices generally used in refrigeration and air conditioning applications. They are capillary tube, thermostatic expansion valve, and automatic expansion valve. Let us see. First expansion device, that is capillary tube. Capillary tube is most common device for throttling in refrigeration and air conditioning system. Capillary tubes are made up of copper or aluminium depending upon the capacity of refrigeration. They are of very small diameter. Capillary tube diameters are ranging from 0.5 mm to 3 mm and the length ranges from 1 meter to 6 meter. Capillary tubes are used as throttling devices in domestic refrigerators, deep freezers, water coolers, and window and split air conditioners. Capillary tubes are connected between low pressure side and high pressure side of refrigeration system. Refrigerant, while flowing through tube, has to overcome frictional resistance offered by the tube, due to which pressure drop takes place. Liquid refrigerant converts into partial vapor, partial liquid as its pressure reduces. The density of vapor is less than that of liquid. Hence, the average density of refrigerant decreases as it flows in the tube. Mass flow rate and tube diameter being constant, the velocity of refrigerant increases since rho into V into A. The increase in velocity or acceleration of refrigerant also requires for pressure drop. Advantages of capillary tubes. Capillary tube is a very simple device that can be manufactured easily and it is not very costly. The capillary tube limits the maximum amount of refrigerant that can be charged in the refrigeration system. Hence, this device does not require receiver. When refrigerant plant stops, the pressure across the capillary tube becomes same. Hence, the refrigerant cycle and the pressure in the system remains constant. Let us see most popular expansion device in refrigeration and air conditioning application, that is thermostatic expansion valve. It is also known as TEV. Thermostatic expansion valve is used as throttling devices in almost all refrigeration application. The figure shows of thermostatic expansion valve. Thermostatic expansion valve is the automatic valve that maintains proper flow of refrigerant in the evaporator according to load inside the evaporator. If the load inside the evaporator is higher, then expansion valve supplies the flow of refrigerant. When load reduces, it allows the reduction in the flow of the refrigerant. It's a block diagram of thermostatic expansion valve. It consists of different parts, that is needle valve, bellows, adjustable spring, adjustable screw, filler bulb consists of refrigerant and capillary tube. During the system is off, the evaporator temperature remains same of the room temperature. Spring force, we are calling it as Fs, acting upward, will push the needle against the orifice. Keep the thermostatic expansion valve closed. So this force we can adjust with the help of screw, and the tension on the spring is being adjusted. As the compressor started, the evaporator pressure decreases at a very fast rate. Hence, the force Fe, that is evaporator pressure, decreases at a very fast rate. Therefore, the difference between the Fp and Fe becomes greater than the spring force Fs. Thus, diaphragm pushes the spring in the downward direction and allows to open orifice. This position we are calling it as valve is said
at the
to
main
be open
components
up.
inside the thermostatic
Let us see
expansion
the
valve,
working
and
of
then we'll have a look at how
thermostatic
the expansion
expansion
valve
valve.
works and why. If we pull apart a thermostatic expansion valve, then we're going to see the following main components. The valve body, which holds the components and has an orifice inside to control the flow of refrigerant. Then we have the diaphragm, which is a strong, thin, flexible material, typically metal, which flexes to apply pressure. Then we have the needle or pin and seat. This moves up and down to restrict the refrigerant's flow path. The spring, which counteracts the force of the needle. And we've also got the sensing bulb and the capillary line, which causes the valve to open or close. As you can imagine, there are a lot of different designs out there for how these valves work. I'm just going to stick with this simple version here to help you understand the basic working principles. So how does it work? Well, as we saw in the real world example, the valve sits just before the evaporator and holds back the high pressure liquid refrigerant from the condenser and controls how much refrigerant can pass into the evaporator. The valve decreases the pressure to allow the refrigerant to boil at lower temperatures. For example, we're used to water boiling at around 100 degrees Celsius, 212 degrees Fahrenheit. That's because most of us live near sea level, so the air around us is compressed by all the weight of the atmosphere above us. However, if we went higher into the atmosphere, say to the top of Mount Everest, then we would find that the water boils at only 70 degrees Celsius, 158 degrees Fahrenheit. And that's because we're higher up, so there's less atmosphere above us to push down on the water, which makes it easier to boil. The boiling is essential for the refrigeration system, as it will absorb the heat from the air or water and carry this away to the compressor. Also, just remember that the refrigerant has a much lower boiling point than water. The high pressure liquid is forced through a small orifice, which causes a pressure reduction, and as it passes through here, some of it will vaporize and the rest will remain as liquid. It's similar to a water bottle spray nozzle. As you pull the trigger, the high pressure water is forced through the small orifice into a much lower pressurized atmosphere. This causes the water to become part liquid and part vapor. This mixture of liquid vapor refrigerant is sprayed into the evaporator, where it will absorb heat from the air or water which surrounds the pipe. In this example, the fan is blowing air across the evaporator. As the refrigerant passes through the evaporator and is exposed to more thermal energy, it will cause it to undergo a complete phase change and will then become a saturated vapor towards the end of the evaporator coil. During this change, there will be little to no temperature change because of the latent heat, and instead it will increase in entropy and enthalpy. The refrigerant will continue to pick up thermal energy, and when it does this after the phase change has occurred, it will then start to increase in temperature. This superheats the refrigerant vapor, and the sensing bulb of the expansion valve is monitoring this temperature to control the refrigerant. So let's have a look at an example. Let's say the cooling load increases. This will cause more refrigerant to evaporate and the superheat will increase, causing the refrigerant temperature to increase at the evaporator exit. We need to decrease the superheat, and we can do that by allowing more refrigerant to flow into the evaporator. So the pin will need to open more to let the refrigerant pass through. Inside the sensing bulb is a small amount of refrigerant which is separated from the rest of the system and constrained in a closed system to the area of just the bulb, the capillary tube, and the power head. The sensing bulb detects the temperature increase, which causes a small internal reservoir of refrigerant to also boil and evaporate. Because the refrigerant is constrained to a small area, it will cause the pressure to increase, and this pushes along the capillary tube up to the top of the expansion valve. This pushes down on the diaphragm, and that pushes down on the pin, which compresses the spring and allows more refrigerant to pass through the orifice. The valve will adjust to find the correct position so that the force on the diaphragm is greater than or equal to the force of the spring pushing in the opposite direction. This allows the correct amount of refrigerant to flow, which decreases the superheat refrigerant temperature at the outlet, and the sensing bulb detects this and equalizes it. If the cooling load then decreases back to normal, the superheat temperature will reduce. The sensing bulb will detect this and will begin to reduce the refrigerant evaporation in its chamber. The refrigerant in the capillary then flows back towards the bulb and the main valve begins to close. The superheat temperature will also start to rise as this happens. Eventually, the valve equalizes out and the correct amount of refrigerant will flow through to match the superheat settings. Now, all of this happens automatically using this type of valve, which is why it is so popular. There are other electronic versions of this valve which can provide even more precise control, but we'll look at that.
So let us see another type of expansion valve, that is automatic expansion valve. The figure is shown. An automatic expansion valve is also known as constant pressure expansion valve. This constant pressure expansion valve were popular in olden days or in industrial applications. In earlier days, the hand-operated expansion valves were available. These valves allow automatic constant pressure in the evaporator. Therefore, these valves are known as automatic expansion valve. As shown in the figure, the diaphragm is balanced between two forces acting on the upward direction and the two forces acting from the bottom direction. The force Fs exerts on the top of the diaphragm. Atmospheric pressure acts on the diaphragm. Therefore, it exerts a force, that is F0, that is equal to P0 into AD. AD being the area of diaphragm. The net downward force, that is Fs plus Fo minus Fe. This is very important. Fe, that is the force acting on the diaphragm, which is equal to the evaporator force. This net force along with the force due to follow-up spring, that is FPS, which we are adjusting with the help of adjustable screw. So this FPS controls the location of needle with respect to the orifice. If evaporator pressure and spring force is greater than the upward force, that is Fo plus Fs, the needle will be pushed against the orifice and the valve will be fully closed. So there will be no transfer of refrigerant from condenser to evaporator. If the evaporator pressure plus spring pressure is less than the Fs plus Fo, the needle will be pushed against the orifice and the valve will be fully closed.